Okay, we've got one more thing to talk about, and then we'll finish up Unit 4, and we'll have a good grasp of how everything in entropy and free energy and equilibrium constants and all this stuff is linked together to kind of tell us everything we need to know about reactions. So the last thing we're going to talk about is the Nernst equation, which is something that kind of pulls together all the things that we've been talking about. So we've been talking about equilibrium constants for a while. We've been talking about free energy for the past couple of weeks, and now we've added in cell potentials and voltaic cells. So we're going to use all three of those things, smash them all into the same equation, and see what we get. All right, so let's link some things together. So the first thing we have to do is we have to kind of write down what all our formulas are. So the first one is for non-standard, or actually let's start with the standard free energy. So standard free energy, delta G naught, is equal to negative RT times the natural log of the equilibrium constant of our reaction. Right? And so this is something that we kind of showed in previous videos. It comes from um, when our reaction is at equilibrium, that means that our non-standard free energy is zero, and so right, we're going to get there. So go back and look at those videos if you want to see the derivation of this, but this is kind of the walking around equation that we're going to use for this. If we know the equilibrium constant, we can figure out the standard free energy. The standard free energy, whoops. Standard free energy also equals negative NF and E cell, the standard reduction potential there, right? So this was our electrochemistry version of the same reaction, right? We had N is the number of moles of electrons that are traveling, F is the Faraday constant, and then we have our standard reduction potential for the cell. And we all remember kind of how to figure that out, right? The standard reduction potential for the cell is the cathode, the reduction potential of the cathode minus the reduction potential of the anode. So that's great. We can figure out the standard free energy. How do we figure out the non-standard free energy? Right, so this is what is the free energy of our reaction if we're not at standard conditions, right? So we take the standard number and then we add in RT times the natural log of Q. And so this tells us if we start changing concentrations, Q tells us, right, Q versus KEQ, right? If we're not at equilibrium, we're going to have different concentrations. So Q, we account for that by having natural log of Q instead of KEQ. We can change the temperature, we can change the pressure, the gas constant is in there, and that allows us to kind of do all this stuff. So non-standard free energy we can figure out from here. What's a little bit more interesting is what can we do in the electrochemistry sense, right? If we have this setup where delta E, or sorry, the standard reduction potential of our cell is related to the standard free energy, can we set up another one where we can do a non-standard free energy, only we can use electrochemistry terms? And of course we can, because delta G naught, our standard free energy, we have a equation that relates these two things together. So I'm just going to sub in NF standard reduction potential of the cell plus RT ln of Q. Okay, that's an equation, right? But not a terribly useful one. That's a lot of calculations that we'd have to do there to get to a standard free energy. And if we know these numbers, then we already know delta G naught. So does this really help us? One thing, so this is what Nernst figured out. So Nernst said that, well, we can, if the standard free energy is equal to the standard reduction potential, we can just say, well, the non-standard free energy is equal to the non-standard, or is related to the non-standard reduction potential. So he says this, he used this E cell only under non-standard conditions, and so I keep saying non-standard conditions, and I think that maybe that's not exactly clear what I mean. Um, when I say non-standard conditions, what I mean is then we can use any concentration we want, right? We can do this at any temperature we want. We can do this under any set of concentrations that we want. And our equation for non-standard reduction potentials, for non-standard free energy, whatever, will allow us, it will have those terms in it so we can figure it out. So basically, when we say non-standard, that just means we can use anything. Like any conditions in the lab can be plugged into this equation. So the non-standard equations are actually probably the more useful ones for actually doing lab work, right? Because we can walk around, we can say, oh, the concentration of this thing is whatever molar, and the concentration of this one is whatever molar, and we can just plug that in and get a number that tells us what the potential is going to be, right? The standard ones, the ones that we've been calculating up till now, are nice because they give us a general sense of what's a cell with a lot of potential, what's a cell with not very much potential, what makes a good anode, what makes a good cathode, that kind of thing. But if we're actually trying to calculate how much energy we can get out of a reaction, we need to be able to calculate it under any conditions we want. So that's why we talk about non-standard conditions, because it really just gives us a broader range of setups or conditions that we can still calculate these values for, right? So non-standard, or not non-standard free energy, this is non-standard reduction potential. Right. So non-standard reduction potential equals the standard reduction potential plus all of our adjustment factors, right? So we're going to adjust for temperature. We're going to adjust for if there's gases. We're going to adjust for concentration of our components, etc. So now we have this equation, and we're almost to the Nernst equation. What Nernst did next is he divided both sides by negative n times F. And so the Nernst equation actually tells us that the non-standard reduction potential of a cell is equal to the standard reduction potential of a cell minus RT over NF times the natural log of Q. Okay. So this is the actual Nernst equation, right? It comes from over here. We're just going to divide both sides by negative NF. So we're going to divide this by negative NF, divide this by negative NF, and divide this by negative N. Okay, so that's the Nernst equation. This is the derivation of it. I'm going to pause this video, and then the next video we're going to do just a couple of examples and kind of interpret what does the Nernst equation actually tell us, right? Why do we need this? What is the big kind of upshot of it? So stick around for that one. It's going to be a good one.